here we go.
How many more chapters do we have this year?
3 or 6 or 7.
3-ish is probably about right for the juniors,
Including this one?
counting this one. Less for the seniors,
Like 2 for the CD.
probably-ish. All right. So here we go. So today we're going to start chapter 15. Chapter 15 is a big boy. In chapter 15, we're going to talk about exponential functions, logistic functions, and logarithmic functions. Woof, that's a lot of stuff. In addition to that, we're going to talk about like some applications into financial mathematics. So we'll be talking about compound interest and annuities and investments and depreciation and appreciation and dealing with some financial application here. So it's got a lot of stuff here in chapter 15. In section 15.1, we're going to start, though, just by introducing us to 2 of the 3 types of functions, specifically exponential and logistic functions. Yes, something is printing. Thank you. So a exponential function is something that can be written in the form.
Oh my gosh.
You're not out there the more today.
It was giving me problems yesterday, and I haven't had a chance to have somebody come in and look at it, so we're just doing it, kicking it old school today.
You do this Sunday.
No. So an exponential function is just something that can be written in the form a times b to the x. We call that a coefficient the leading coefficient. And a can have any value except for 0. We call b the base of the exponential. B can have any value except that b must be positive and not equal to 1. And then x is the exponent, and that can take on any value. Does everybody feel okay here? Why do we not allow the leading coefficient to be 0? And that would be a constant function, right? Everybody agree?
Yeah.
Why do we not allow the value for b to be 1?
Because isn't 1 to any exponent just 1?
Yes, 1 to any power is 1, and then 1 times a is just a, which would mean we'd have a constant function again. A little bit more difficult. Why do we make b have to be positive? Why can't b be a negative value?
Because when a negative number to any power be imaginary.
Well, a negative number to some powers are imaginary. Specifically, the powers that we want are the ones where, or the powers that are a problem, are the fractional exponents whose denominator is even. For example, 1/2 because we know 1/2 is the same thing as a square root. So that's why we have the b values must be positive, because we don't want to accidentally have a bunch of undefined results here. Does everybody feel okay with what this is going to look like? Okay. So our exponential functions have a specific key feature. All exponential functions of the form y equals a times b to the x have one horizontal asymptote at y equals 0. That means they are either going to look like something like this, or they could look something like this, or we could look something like this, or we could look something like this. Yep, they are all going to look exponential. So the end behavior for these, I'm going to color code the end behavior based on the color of the graph that I did here, right? So I'm going to draw 4 sets of end behaviors, one in blue, and in green, and in red, and in orange. Everybody's okay? So in blue, so that first end behavior represents the left end of the graph, right? The left end of the graph is going to negative infinity in the x direction. And what y, or where is that end of the graph going in the y direction?
Negative.
Talking about this, it's going to y equals 0, because it's following the x-axis, right? What is the right end of that graph going to in the y direction? Positive infinity. Now let's look at the green graph. That first end behavior is representing the left end of the graph. What is that left end of the graph pointing to in the y direction? Positive infinity. And how about the right end of the graph? Going to 0. Mary, it's because Addie, it's because it looks like that arrow is following the x-axis, right? Do you agree?
Yeah.
The x-axis is the line y equals 0. Does that feel okay? Okay. Sorry, I couldn't tell which lady was the one asking the question, Mary. I thought it came from that direction. That's okay. You don't have to apologize for me not recognizing the voice of who it was.
Wait, which orange is this for?
Well, one is orange and one is red.
Oh, both of them are orange. Oh, I see.
This is red, what we're doing right now.
Yeah, that looks. Am I the only one or?
Should I?
No, I can kind of see it. If you write in your computer, if you're.
Oh, it's easier to tell when you do it orange.
That's orange. You might be colorblind.
Nah,
I was getting scared for a second.
I was too, but now it's easier.
Okay. I'll let Mr. Little know so he can commiserate with you, fellow colorblinders. All right, if we're talking about the red graph, this is the left end. What is that pointing to in the Y? Very good. And then what is it? What is the right end pointing to? Negative infinity, that's correct. On to orange, the left end points to, and the right end points to. Does everybody feel okay with the end behaviors here?
Yeah.
So the point is that unlike a rational function where both the left end and right end of the graph follow the horizontal asymptote, for an exponential function, only one end is going to follow, right? The other end is going to go off to either positive or negative infinity. Does that feel okay? Yeah. All right. Let's talk about just evaluating. So let's say we have f of x equals negative 2 times 4 to the x. Is this an exponential function?
Yes.
Yes, right? It fits the form that we defined earlier. Before we go on, this is like an aside. So I'm going to ask you true or false. Negative 2 times 4 to the x equals negative 8 to the x. True or false?
I think it's.
I heard both trues and both falses.
Because wouldn't negative 2 also have to have an exponent of.
I'm pretty sure it's false, because you can't, that's not how exponent rules.
Yeah, the exponent rule that we would need for this is this one. So in order to multiply the bases together, the exponent must be the same. The exponent on the negative 2 is to the first. The exponent on the 4 is to the x. They are different exponents, so you cannot multiply the bases together. Is everybody okay with that? One of the most common mistakes students make in this chapter is they do that, which is very bad.
If it was like 4 to the second, could you?
Nope. No, so if I had this, there the bases are the same, so I could add the exponents. That's okay.
Oh.
Or if I had here where the exponents are the same, that's fine. I can multiply the bases. But if either the exponents are different or the bases are different, there's nothing to do, which is what we have in the above example.
For the one where you multiply, like the bases are the same,
Mhm.
or with the second two,
So like if I have 2 times 4, that's 8, right? So 2 to the first and 4 is 2 to the second, right? That should be 2 to the third, which is 8.
Okay, so just one.
Yeah,
Or just like one number.
that's basically what's going on. Does that, when I put regular numbers in there, like, okay, yeah, that makes sense. Sure.
So, cause that, it's just X.
Yeah. Does that feel okay? All right. Okay. So I have this function up here, f of x. What if I want to say evaluate and do f of 2? What does f of 2 mean?
F of 2 means that you sub in x.
Yeah, plug the 2 in for the x. And then, according to the order of operations, what operation should I do first? The exponent goes first.
There we go.
Everybody feel good? We're going to do a couple more of these just to make sure that we're square on our exponent rules and order of operations and all that jazz.
Oh, this one would be 0.
Well, wait. That makes sense. I don't think this one would work.
It does work.
First year math. Oh, not.
Oh, wait a minute.
Anything to the power
4 times 0 is 0, and 0 times negative 2 is 0.
It's not times 0, it's to the power 0. And Sebastian, you're almost right. There's one exception to that rule. Anything other than 0 to the 0 power is 1. 0 to the 0 is undefined.
Is this speaking to you? No? Are you picking up what? No? So would you be able to just put this in your calculator and spit out even an answer?
Yes, but if there's variables involved, you can't really do that. So that's why
Yeah.
we're practicing the rules with numbers so that we get a feel for how things need to work still. Because you guys tend to do better with numbers than you do with symbols.
Right.
So I'm going to give you numbers first. Does that feel
Yeah.
good? Okay, but yes, in general, anything other than 0 to the 0 power is 1. That's a rule of exponents that you would have learned last year in Algebra 2. That's an expectation of something that was a mastery level skill, because you would have seen it in Algebra 1 and Algebra 2 for a second time. After the second time, the expectation is that those things are mastery, and we remember those. Now, I don't mind reminding you, but that needs to be something after I remind you that, like, oh yeah, I remember doing that. Okay? It's okay to forget it the first time through, but like it has to come back, like all these other exponent rules that we're kind of using here. That won't be the last one. Okay. So if I want to do f of negative 3, what am I doing here?
Subbing in negative numbers.
Now, how do I do 4 to the negative 3?
Well, wouldn't it be positive? It would come out positive.
What does a negative exponent mean? What does that tell me to do?
Well, you're multiplying by the negative, right?
Nah, man.
Shoot, it's meant to like this.
It makes a reciprocal.
Oh,
Right, yeah. Remember that.
oh.
Are you good?
So again, there's another exponent rule that we expect that you remember. You might need to be reminded, but after being reminded, I'm going to expect that you remember that negative exponents make reciprocals from here on out. Okay, won't be the last time you see it this chapter. That's part of the reason why we're doing these examples.
Is there any way we can move the TV a little bit?
Huh?
Is there any way we can move the TV a little bit?
Why don't you just change your desk?
No.
I mean, that's way easier for me.
I like my desk.
If you just like, well, scoot it over then or something.
I don't know, I like my desk. I like the spotted symbols, you know?
But you just said you didn't like
It's
it because you
comfortable.
had.
It's comfortable here.
Okay. All right, if I'm doing f of 1/2, what happens here?
I don't know.
Man, it's the same thing, right?
You substituted the X.
Yeah. What do you do with a fractional exponent? How do you deal with that? Yes, so fractional exponents indicate a radical. And the rule here is that the denominator of the fraction is the index of the radical, and the numerator of the fraction is the exponent on the radicand. That's the fancy word for the number under the radical.
Yeah.
I'm guessing you didn't remember that because most math teachers don't remember that name.
So if it was like 2/3, that'd be like 4 to the second. And then
It would be the cube root of 4 to the second.
yeah, and then the 3 on the, like where the 2 is.
Correct. Here we go, getting crazy.
You like that. Very I'm such
What do we do?
Don't you post one around the radicals?
Well, we start by doing this, right? Just plugging in for x.
What happened? No. Wouldn't the radical be
So, this is the way that I'm going to think about it in my mind. When I really see this, -3/2, I'm going to think about it as 1/2 times -1 times 3. Is everybody okay with that?
Yeah.
Okay. So when I have a multiplication in my exponent, what is the rule when I have multiplication in my exponent?
I don't know.
That means it was the exponent of an exponent. So I'm going to think about it this way in my mind. Why did I choose this particular order? Does it matter the order that I multiplied those three things together by? It doesn't, right? Why do you suppose I chose this particular order?
So you do the rules from the
Well, what's the innermost, what's the exponent to 1/2 mean? Can I do the square root of 4? Is that easy?
Yeah.
Yeah. Okay, that gets rid of the radical. What's the -1 exponent do? Yep, makes the reciprocal. And then how do I do the exponent of a fraction?
Don't you?
Exponent of the top and exponent to the bottom? Daniel?
For negative, for 2/8, how did you, isn't, whatever, isn't 1 to whatever exponent, isn't that just 1?
Yeah, and then you
Oh.
Right, and then I multiplied the -2 in.
Makes sense.
All right. Yes, go ahead, Dan.
So, did you take a your handy Oh, you have to go. Why did you just go on? Well, you just had a journal. The journal. What was it about? Oh, you did the
Oops.
practice.
We're using X's.
No, you didn't do that. What practice? I don't remember what is he doing?
I'm just summarizing the exponent rules that we just kind of observed or recalled from our previous classes. Oops. So these are your exponent rules that we just would have kind of gone over. Everybody's okay with that? Again, none of these should look unfamiliar to you. These are all the rules that we just kind of encountered in doing that. And then maybe a couple of the stray other ones that didn't come up, I tacked on there at the end also. All right. It's all on the OneNote too, right? Just leave a space in your notebook and come back and grab it. You know? I mean, I wrote pretty stinking slow.
I just was trying to like comprehend what was going on.
Okay. All right, what we want to talk now is about how we go from points on an exponential function to an equation for the exponential function. So there's two situations. So situation one is we're given a table of points. And our goal is we want to be able to write a y equals a times b to the x equation. So we need to figure out a value for b, or for a, I should say, and a value for b. Is everybody okay? Once we found the value for a and b, we're done. So the best case scenario in this is where we have when x is equal to 0. That makes us very happy. Let's see what happens when I plug in x equals 0 and y equals 3 into my equation. Everybody okay here?
That's not good because B is equal to 1.
What's b to the 0? Unless b is equal to 0. Do we know b can't be 0?
Yeah. Why not?
Yes, we do. How do we know it can't be 0? If we're writing an exponential function, can b be 0? No! So we were basically told that b can't be 0 because it asked us to write an exponential function. Is everybody okay with that? So we're good, right? So A is 3.
I thought B can't equal.
B isn't 1. B to the 0 is 1, which is fine,
Oh.
right? B isn't 1. B to the 0 is 1. We still need to figure out what B is, but we have A for free, which is awesome, right?
Did you just guess which one to do first?
No. I took advantage that one of my points had the x-coordinate 0. If I have that, this is a much easier problem. We're going to look at situation 2 when I don't have that and how we handle it then. Now, what I'm going to do is I'm going to pick a second point. Does it matter which the second point is? No. But I'm going to pick the one that's going to be the most convenient. If I have x equals 1, that's the one that I'm going to use. So I'm plugging in the point 1, 15 into x and y, and my answer for A into A. Is this an equation we can solve for B? How do I solve for B here? Oh, divide by 3. Yeah, subtract. Oh, it hurts. You should be.
Yeah.
So my answer can be y equals 3 times 5 to the x. Is that the same as 15 to the x? Right, I can just say this, right? No, of course not. Very bad, don't do that.
Yeah, very bad.
That's our answer. Is everyone okay there? So if you're given a table, what's the first thing you look for? Do you have x equals 0 in the table? If you do, use that point to get A, and then you use your answer for A and any other point to get B. Done. Should be relatively easy. What if we don't have a point where A equals, or where x is 0? Lily, what's up?
May I use the restroom?
Yup. Sure. Okay. Good luck. Score some goals. Or stop some goals. I don't know where you play. It's tough when you tell the goalie to score some goals. They're like, Don't really do that. All right. Notice this one. Do I have an x coordinate of 0 for any point? What am I going to do? I'm going to build a system of 2 equations. So I'm going to use my first point. And then I'm going to use my second point. And that's going to form a system of 2 equations. I'm going to refer to the first equation as equation A, and the second equation as equation B, just so that I have a way to write down some work on my paper so you guys understand what I'm doing. You don't have to name them anything. That's what I'm going to name them. Everybody's okay? Now, notice what operation is going on between my A and B variable here. Multiplication. When you solve systems in Algebra 2, what operation was going on between the variables? Addition or subtraction, right? So in Algebra 2, when you had addition and subtraction between your variables, to do elimination, you added or subtracted the equations. If my operation between the 2 variables here is multiplication and division, what am I going to use to eliminate a variable from the equation? Multiplication and division. Okay? So what I'm going to do is I'm going to pick the equation that has the bigger exponent of b. Which one is that, equation A or B? B, right? -1 is bigger than -3. And I'm going to divide it by the other equation. Oh my God. I wrote the wrong thing though. It should be equation B divided by equation A, right?
Does that matter?
Yeah, it makes life easier if you always do the bigger exponent of B divided by the smaller exponent of B. I guess it doesn't matter, but it matters to, it should matter to you because it makes the problem a little easier to deal with. So if I have B divided by A on the left-hand side, I'm going to have 12 divided by 48. And on the right-hand side, I'm going to have A times B to the first divided by A times B to the third. Is everybody okay with the setup that I've got here? Look at that right-hand side of the equation. Do you notice that anything you can do there? I can reduce the A's. And then how do I deal with division of numbers that have the same base but different exponents? What was the rule of exponents I used there?
Subtract the exponent.
Yes, I subtract the exponents. Very good, Nick. So I'll reduce 12 over 48. And that's going to be the top minus the bottom exponent. What's -1 minus a -3? What's that equal? 2 is correct. Is everybody so far so good? Okay. Now what do I need to do to solve for b here? I have b squared.
Would you square both the 1 and
We'll square root both sides, right? When I square root both sides of the equation, what does that generate?
B.
What do you have to remember? When you square root both sides of an equation? Plus or minus. Now, what's the square root of 1/4? It's the square root of 1 over the square root of 4. What do you notice, though, here? Go ahead, Adriana. You're welcome.
That's B.
Yup. Do you notice anything funny here, though?
Not being negative.
Ah, very good. Remember, back to the very beginning, that value for b has to be positive and not equal to 1. So well, guess what we can do? we can discard the minus from our plus minus. So we have, I know the b is 1/2. Now that we have this, we can find the a. So we can take either equation A or equation B and plug in our value for A and solve. I'm going to choose to use equation B because the exponent on B is closer to 0. Is that 12? Okay. Hey, Mr. Sharp.
Gotcha.
Thank you, my good man.
Okay, welcome. Thank you.
Is everybody okay with how I plugged everything in? What's 1/2 to the -1? 2 is correct, Gabby. How'd you get 2? Mm-hmm. So when we divide both sides by 2, we get a equals 6. Put those two together. And there's my final answer. Questions on what I just did here? That was rough though, right?
Yeah.
Want to know a secret?
Well,
Calculator can do this. Who's interested in that?
I'd be very interested in doing that.
Right? So if you have your graphing calculator with you and you'd like to follow along, I invite you to take it out. If you'd like to follow along but you don't have a graphing calculator with you, you can borrow one of mine.
Silence. You cut off. What?
All right. So who remembers the modeling chapter we did way at the beginning of the semester? It's like, what would it have been? It would have been like chapter 12. You guys, who remembers chapter 12?
Took it away.
Maybe if I show you the problems, that'll,
What was this one? Like,
where we give you the tables and you build the regression equation.
yeah.
Guess what I'm going to do here? I'm going to do the same thing. I'm going to take this data table and build an exponential regression for it. So where do I go to type in my data? Stat, edit. I use L1 and L2. So in L1, I'm going to type my x coordinates, so -3 and then -1. And in L2, I'm going to type in my y coordinates, so 48 and 12. Once I've done that, I'm going to exit back out to the main screen, so second, and then the mode button, which is right next door. Then what do? I need that exponential reg command. Where did that thing live? It lived under stat, and then calc, and then I scroll down until I see exp reg. That's it right there. I press enter. I'm going to do that on L1 for my x's and L2 for my y's. And I'm just going to hit calculate. And look at what it tells me. It tells me this is y equals 6 for A times 0.5 b to the x. Is that not the exact same thing that we just wrote?
That's the same. Wait. Why doesn't that like the R squared or the
Do you think it's?
Do you need them?
No.
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 Oh,
So don't worry about it. Who's happy with that? Is that okay? Yeah, I thought you'd be pleased with that. Isn't it nice when, like, here meets your old skill, we can use this to package and do something new?
yeah.
Yeah, right? That's rad.
Brad, get it.
All right. So, the next thing I want to talk about is a special number. And that special number is a irrational number. So just like the irrational number pi, we give a symbol to represent it, right? Pi is what number approximately? 3.14. This irrational number that we're going to talk about has a symbol. That symbol is E. Which is about 2.72. We call this number the natural base, or sometimes we name it after the mathematician who discovered this. That is pronounced Euler. I believe he's German. Might have been before Germany was a country that he was working. Germany's a relatively young country by European standards. Like, I think post-US Civil War, Germany wasn't a country, just became a country. Before it was like Bavaria or Prussia or a bunch of other things. Like there was no state of Germany until like the 1860s or 70s, I think.
Germany was a modern nation state on January 1860.
Yeah, look at that. Way to go, Mr. Kulik. You don't even teach history.
Switch it up.
What?
Switch it up.
Then
Oh, are you good?
So there you go. All right. So what is the power of this number, right? We'll talk about that a little bit later. The way this number is formally defined, though, is this. And we'll talk about that when we talk about compound interest. We'll circle back to this and talk about like why this number is important. But that's the gist of it. So you notice when we write our exponential functions, that base b could be anything, right? It's okay with you guys, right? That sounds right. Well, it often makes it difficult to compare two different exponential functions if their bases are different. So one way that we can make that comparison easier is if we write all of our exponential functions so that they have the same base. One way we can do that is using that base to have the value e . So if we compare now, actually, before we do that, let's say that. So this is like just another alternate way we can define this, okay? So we're going to define a exponential function as exponential growth if the function is increasing as we move from left to right. And we're going to define a function as exponential decay if it's decreasing as we move from left to right. Now, ideally, we'd like to be able to look at our equation for our exponential function and be able to tell if it's exponential growth or exponential decay just from looking at the equation and not have to generate a graph for it. So to do that, if I look at something in the form y equals a times b to the x, actually, I'm going to call this, like, I'm going to name this 1 and 2 so you know which situation goes with which picture. So I'll call this 3 and 4. And if I instead had written my exponential equation in the other form, a times e to the kx, Is everybody okay with what I've written down here? So if I asked you, if I write down an equation and ask you if it's growth or decay, you should be able to tell me using this criteria. Let's do a couple of examples. So if we have y equals a time, or negative 2 times 3 to the x, my a is negative 2, so less than 0, and my b is positive 3, greater than 0. Or I should say greater than 1. So it's decay. If you looked at the graph on your calculator, you would see something similar, right?
Yeah.
So let's look at this one. Notice this is in the form with the e. That's that situation, right? You guys cool with how I'm deciding if things are growth or decay?
Yeah.
Just looking at the values for A and B or A and K and then using the criteria we've outlined here. There's nothing more to it than that. Everybody good? All right. Let me grab our next example from the notes because it's like a story problem and I'm just not about writing all these words down by hand. Here we go. Bye, Addie. Good luck today. No more ties, okay? All right. You don't suck, you're just not ready. All right. So it says, given that the population in a certain city in 1990 is blah, 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 and the population of the same city in 2000 is yada, 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 and assuming the population growth is exponential, in what year will the population reach 1 million people? So it's going to be a two-stepper. So this first sentence is basically saying, take the point and the other point and put them together to spit out an exponential equation. Now, as Sebastian's noted, probably worth doing this as a calculator problem because we just saw how to do this. Come on. So stat, edit, 1990, and then 2000, 72248. and 895,193.
Thank you.
You're welcome, Alice. Have a good day.
You too.
Everybody happy with what I entered? Okay. So now stat, calc, exp reg. Now I'm going to do something different here because I'm also going to use the store regeq command. Do you remember what this does? It saves the equation into one of the y1 spots or one of the y equal spots so we can look at the graph of it later. And I'm going to use that to do the second half of the question. So I'm going to save this into the y1 spot. So to get a y1 here, I'm going to press vars, go over to yvars, pick function, and then y1, and press enter. If I go and I look at the y equals, you notice that it's gone ahead and put the whole equation in here for me, right? And I should have written this down first. All right. So my function then, f of x, is equal to, what's the value for a? No. Keep reading.
1.7277.
No.
To the negative.
Yeah. So it's going to have 5 zeros out front. And really, we should try to hang on to a lot of these decimal places because exponential functions are pretty temperamental. So I'm going to just, in my calculator, I'm not going to do any rounding. On my sheet of paper, I'm just going to eventually quit. But I'm going to give 5 significant figures or something on these. Everybody okay there? With how I interpreted that? Now, what's it want? It wants me then in the second piece to solve when f of x is equal to 1 million. Is everybody okay with the two parts in the question? What part 1 and part 2 is asking for or getting us to do? So to solve f of x equals to 1 million, I'm going to do that by graphing. So I want to find the place on the graph where this function intersects the line y equals 1 million. Is everybody okay with that? Now I'm going to have to be careful about choosing my window because if you just hit graph, you're going to probably see a fat lot of nothing. So I'm going to go to the Y or the window key here, and I'm going to think hard about my graph. What time does my situation start at? What year? Okay, so that'll be my first year. What other piece of time information are we given? 2000. From 1990 to 2000, we gained about how much population? Go look at the numbers. It was like about 100,000 or so, right? Yeah. So my guess is I'm going to need at least another 10 years to top over 1 million because we're just shy of 900,000. So I'm going to go like 30 more years. Make sure that I have enough space in there. Is everybody okay with my reasoning? I'm just making an estimate, and I'll go up by 5s or something. Now the y's are my population. What was the smallest population I had? 700 some thousand, right? Like I'll use 700,000 then as my y min. Did I do, that's 7 million. There at 700,000. Okay. And what's the biggest population I care about? 1 million. But I have to be north of that because I have to see it cross. So I'll do like 1,000,002 or something. And let's say that'll go by 100,000s. Is everybody okay with how I set my graph? This is typically the hardest part for students, is choosing a window. If I hit graph now, the blue is my exponential curve, the red is the 1 million line. I'm interested in the intersection, so to find that, I press second and the trace button, and I'm going to choose the intersect command. I have only 2 curves, and they only intersect in one place, so I can just press enter 3 times, and it appears during the year, or in between the years 2008 and 2009, right? So I have to be careful about how the question is worded here. So I would say x is equal to 2008.2 something. So I would say during the year 2008. Is everybody okay with that? If it asked, in the beginning of what year will the population reach 1 million? Will be at least 1 million people. I would want to answer then 2009, right? Because at 2008, it happened, or might get north of 1 million after 2008, the first year where I have population north of 1 million. On January 1st is 2009. So depending on how the question is worded, will tell you whether you want to round up or round down kind of on that question. Mm-hmm. Does everybody feel okay there? All right. What's going to be the downside of modeling population this way with an exponential function? What's the end behavior for an exponential function? Right? As x goes to infinity, y goes to infinity. Can populations go to infinity? No, right? What happens? Well, eventually you run out of resources, right? And you can't support any more population. It has like a carrying capacity. So ideally what we'd like is a function where, we have like a lower limit at like 0 and we have an upper limit, and the function acts exponential while the population is small, and then like levels off when the population starts getting big, close to that carrying capacity, right? Does everybody see why this would really do a nice job of describing population? So this is called a logistic function. So logistic functions are written in the form So this has, logistic functions have 2 horizontal asymptotes, one of them at y equals 0, the other at y equals c. We refer to y equals c as the limit to growth. That's like the carrying capacity for our population. So let's look at another example now of a story problem where instead of using an exponential model, we'll use a logistic model. Everybody okay with that plan? So again, kind of a lot of words, so I'm just going to use the screen cap to drop this boy in here. So this says the population of a city can be modeled using the logistic growth equation P of T equals yada yada yada, where P is the population of the city T years after 1950. So that's a really important phrase in there because that tells us how we have to change our value for t into a year. So the year in question is going to be t plus 1950, right? So whatever we solve here. And then the question asks us, at the beginning of what year? So that means round up, no matter what, will the city have population 1 million people? So that's the equation that I'm going to be solving. So again, how am I going to do this? On my calculator, I'm going to go ahead and type in my logistic equation here. Is everybody okay there? So I've just typed this in exactly like it looked like on our sheet of paper. I'm now going to set a window. So my x-min should be 0, which represents the year 1950. I don't know how long this is going to take, but I'll assume by the year like 2100, I don't know how big this city was, but I'd assume that's going to be enough time to get north of 1 million people. So 2100 minus 1950 is 150. And then say, let's go by tens or something. That's 15 tick marks. That ain't bad. My y minimum should be 0. That's the lower horizontal asymptote. And my y max should be the upper horizontal asymptote, which is the numerator of the fraction. Now, I'm not going to type that all in. I would say 100 or like 1.5 million is close enough for us. So I'll do that. And then let's hit graph. So there's my logistic curve. Notice that nice classic S shape there. And there's my intersection. So second trace, intersect command, enter, enter, enter. So my t is a little more than 79. No matter what, I'm rounding up. So my year is going to be 80 plus 1950, which means in the year 2030 is going to be the first year that at the beginning of the year I have a population of 1 million people. How's that feel, dudes?
Good. Easy as fuck.
All right. If you say so. So you guys should be able to do 1 through 16 at this point. Is that due this Sunday?
No, the Sunday after.
Yes, you got it. All right, I'm out. Good job, guys.